Howdy, y'all. Welcome back to the channel. My name is Professor Parks, and I will be continuing my lecture series on the solar system. Today, I'm going to be talking about the nature of science. So, last lecture, and if I remember, I'll put one of those title card thingies in the description or wherever. Anyway, thinking about too many things today. Last time I talked about the nature of astronomy. Essentially, that astronomy asks the big questions and why I think that astronomy is important as a field of study. Today, I'm going to be taking a more general approach. I'm going to be talking about the nature of science itself and really talking about trying to distinguish what science is, what it does, and what it cannot do. And I will be giving a case study of one of my favorite subjects, exoplanets, as an example of how science is done over time. And sometimes some of these questions that we have don't get answered until decades later. Or in this case with exoplanets, even centuries go by between first postulating the question and then finally getting an answer to it. And there are obviously going to be roadblocks and stumbling blocks all over the place. So let's get into this. So apparently StreamYard does not like animated title slides. So yeah, it had a nice, cute little radio telescope spinning or moving around. It was awesome. Anyway, you'll have to take my word for it. Before we get into that, one of the things, particularly since this lecture series is primarily focused on the solar system, one of the best videos that I've seen on YouTube when it comes to explaining the scale of things is this one, is the link that I have here. Again, hopefully I can remember to post in the description. This is a group of, howdy Clive, welcome to class. This is a group of folks who went to the Nevada desert in order to properly build a true scale model of the solar system. And what I mean by that is that, as they mentioned in the video, if you were to look up on your computer, give me a scale model of the solar system, you'll only find one of two things. Something that is to scale by size or relative to size, say the size of Earth relative to the true size of Jupiter, or they can show you relative size in relation to distance. The two of them cannot be, it is impossible for you to visualize those on a computer. And so because they had to go on, because as you'll see if you watch this video, in order to get everything to size where the sun is literally a meter in size and everything is based on that, Neptune is 21 kilometers away. Oh. No, I believe that is too far. Anyway, you can find out. I've forgotten, but it's very, very far away. So please definitely make sure of that. And also, this is a bit old, but I love this. I actually have a clock of this, made of this. This is done by Eleanor Lutz, who at the time, I'm sure she has her PhD at this point, but at the time when she made this was a biology grad student. And one of her passions is the visualization of science. Howdy, Alan. The visualization of science. So what's represented here is at least to what it was known in the mid-2010s, every solar system object that we know of, and the mass amount of things are asteroids and comets. So if you look, you could, I don't know if my pointer is visible, but these big bright dots with little trails, single trails behind them, those are the planets. But all those teal dots, the reddish dots, the green ones on the outside, all of those are small body solar system objects, asteroids and comets or Neptunian objects. And so while the planets are generally the biggest focus of any astronomer or any person really looking into astronomy, when it comes down to what is actually in our solar system, the vast majority of it is the small stuff. And actually, that's a reoccurring theme within astronomy. So I want to read you this quote because I think it is extremely apropos to what we're going to be discussing today. This is by Einstein, who is an eminently quotable individual. He says that all knowledge of reality starts from experience and ends in it. Propositions arriving at by purely logical means are completely empty as regards to reality. Because Galileo saw this, particularly because he drummed it into the scientific world, he is the father of modern physics, indeed of modern science altogether. Later on, I'm going to be talking about or discussing the Copernican revolution. The Copernican revolution was a transition between the geocentric universe, or the geocentric, the dominance of the geocentric universe as the prevailing worldview, to the heliocentric universe. And really, what this actually, the core of it, or the sort of the, if you really read between the lines, what this revolution was a departure from propositions that were arrived at purely by logical means to ones that were arrived at experimentally. Specifically, Aristotle. The philosopher Aristotle, dominated our scientific worldview, or at least the viewpoints of Aristotle and how Aristotle came to these points. That dominated scientific thought up until the Copernican revolution. And really, Galileo was while it's named after Copernicus, Galileo, at least in terms of the process of science, Galileo is really the person who broke us away from that just purely logical framework. So how do we distinguish science from non-science, or say pseudoscience? Simply looking at a textbook definition, be it Webster's or what have you, is inadequate. Because what we find is that science, just from the word itself, comes from the Latin, which I'm going to mispronounce, scientitia, means knowledge. Now, obviously, not all knowledge is scientific. I mean, you can have the knowledge of love, the knowledge of poetry, the knowledge of emotion, emotional knowledge, artistic knowledge, these sorts of things. So science does not have a monopoly on knowledge. So we need a better understanding. We need a more specific definition of a way of describing science. Before I have, and this is a practice that I do in really anytime I have a discussion, particularly with someone that I know where that person and I do not see the world in the same way. And it tends to probably annoy people. But anyway, I like to start off by defining terms, having an agreed or an acceptable base or collection of words that we both understand what these things actually mean. He's a demarcation question. Popper gave a very falsability. Yes, well, I will get into that. Clive mentions. Yes, it's Popper, not Pooper. Karl Popper is one of the key philosophers, as it were, on the topic of the process of science. But I like to, like I said, I like to define what I mean by certain terms. And I think particularly in this arena, this is vital because certain terms that get tossed around mean very different things to a scientist and to a layperson. Now, you may not agree with these terms, but these are the terms that I'm using, and these are how I define them. A fact is something that is a result of an observation or a measurement. It is not biased by anything else. I am 6'1", or 181 centimeters, 182 centimeters. I can measure that, I get 182. Let's say 182. I measure that, I get 182. Clive, if Clyde measured and I was in the UK, he'd get 182. If I were on Jupiter, I'd get 182. If I were in the Andromeda Galaxy, I'd get 182. This is something that is definitively observable, definitively measurable. Hypothesis. A hypothesis is an idea leading to testable predictions. It is, in essence, a question. But it is a question, in order for it to be a hypothesis, it has to be a question that can be answered given rigorous testing. It has to be a question that can be falsifiable. A law. A law is an explanation, usually in a mathematical form, that describes a certain natural phenomenon, such as Boyle's law or the law of gravitation. This is something that describes a very particular phenomenon based on very particular variables. Now, the most contentious term that I've found is theory. It's also the most by contentious, I really mean misunderstood. Now, I am going to go to the dictionary just to kind of prove a point. According to the dictionary, and I'm going to start off with the number 6. This is the definition that I think most lay people use for theory. And that is a contemplation or speculation, such as I believe that Jeffrey Epstein was killed by the Clintons. I have a theory that Jeffrey Epstein was killed by the Clintons. This is an idea. This is not something that can be testable. It's not something that you can measure and come up with quantifiable results. It really also doesn't describe anything, any kind of physical nature of the universe. The proper definition from a scientist's point of view is a coherent group of tested general propositions commonly regarded as correct that can be used as principles of explanation and prediction for a class of phenomena. So the classic theory is the theory of relativity. Theory of relativity basically describes the motion of objects within gravitational fields that deal with objects that aren't really, 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 really small. And that is the realm of quantum mechanics. The point that I really, really want to really want to hammer in is that from a scientist's point of view, a theory is not just a good idea. A theory is a theory has a number of things that it predicts and a number of different phenomenon that are all physically related to each other. All of these predictions have been proven proven is a bad word. All of these predictions have either not been able to be tested due to, say, technological limitations, but more importantly, those that have been tested have not been falsified. There hasn't been a single test as of yet that says the theory of relativity is simply wrong about any particular subject. So right now, it is our best explanation, it is our best description of the physical universe, how things move within a gravitational field when things are at the macroscopic level or really, really big. The reason why I didn't like proven is that in science, nothing is proven. And by proven, what I mean is that it is an irrevocable, it is a absolute fact. There is nothing that is, it is not wrong. It can never be proven wrong, or it can never be shown to be wrong. Science proves nothing. What science does is it gives you the best explanation possible within a certain confidence When you dive into science, scientists will always couch their results with error bars. I know that the age of the universe is 13.8 billion years old. Actually, in fact, it's 13.8 plus or minus, I think, 2 billion years old. There's always an error bar saying that number is as close as we can get, but it could be slightly off one way or the other. Science is also provisional. As I'll describe later on, an entire theory itself can actually be replaced. if there is enough falsifiable evidence to suggest that it just doesn't adequately describe the universe. The best example of that in physics is the revolution or the change from classical mechanics, that which was built upon Newton's work, to the theory of relativity, that which is built on Einstein's work. So I have a few hallmarks of science. I have a few hallmarks that will lead us into a better understanding of what science, how to best describe science. The first thing, and I think the most important thing, is that science is a exploration. Real quick, what if you were moving past me at a considerable fraction of the speed of light? Many things would happen. Many things would happen. Science is an exploration. If you are in a field of study, or if you encounter a field of study where there are no open questions, where the process itself has no open questions. Let's take astrology, for example. Not astronomy, but astrology. Astronomy purports to know that human behavior can be predicted via the mechanisms of the stars, by the movements of the stars and planets. From what I understand, the open questions are what's going to happen to you if Mercury is in the house of Aquarius, or what have you. But the mechanisms, the mechanics of astrology and how it works, there are no open questions. Astrology will tell you that the system itself is complete, that it works, and there's no more reason to look into things. That is not science. Science is always looking science always has questions about how things work, how things are described. Even when we think we know them very precisely, there is always work to be done to either make our knowledge more precise, or to falsify it, to figure out that actually no, the universe is not expanding at an ever increasing rate. Most of the scientific fields their work is done through controlled experiments, where they are in some sort of laboratory, or their survey is done with a certain group of people, and they have control over the variables that might affect the outcome of the question. So, like for physics, for example, I'm really bad at analogies. So you have an experiment, and you want to know how it let's say the Cavendish experiment, for example. Cavendish's experiment in one way can be used to determine the gravitational constant. Basically, you have a system of masses, and you want to see what the power of attraction is between them. There are other conflating variables, like these masses can be affected by magnetic fields. The process can be affected by temperature, by humidity. And so the experimenter has to take these variables into consideration and control them so that these do not affect the results or interfere with answering the question that they're trying to answer. Astronomy is different, as I pointed out in my first lecture. Astronomy is an observational science. My apocryphal number is around 95% of all astronomical knowledge is derived or is arrived at through the collection and manipulation of light. There is no way for us to go to a galaxy, put it on a scale to find out how much it weighs. The only way that we know how much mass is within, say, the Andromeda Galaxy is by looking at the light from the stars, from the gases in that galaxy, and then using very clever means to derive at that question. One really, really nifty experiment, which actually I'm hoping to be able to replicate within the coming year, particularly about April of 2024, is the experiment by Arthur Eddington when it was the first demonstration that relativity may be onto something. And what he did was he used a solar eclipse to demonstrate that light does in fact bend around a mass in spacetime. He used the virial theorem. 2. Science only seeks explanations in the observable universe. We do not seek explanations that are metaphysical, divine, theological, or what have you. The explanation for why thunder happens is not because Thor got angry and is smiting somebody. We must, modern science, or really science, seeks explanations that can be verified, can be seen in one way or another, and not just simple, God did it. One of the things that scientists has to keep in mind is something known as Occam's razor. I still don't know what razor is in this context, but Occam apparently was, I believe, a monk somewhere down the line. And one way of phrasing what he said was, if two hypotheses explain all observations equally well, then we should use the one that requires the fewest assumptions. Or as my father used to say, keep it simple, stupid. A great explanation for this is, again, going to the Copernican revolution. At the heart of the Copernican revolution, at the height of the Copernican revolution, you had two competing hypotheses. You had the Ptolemaic model, and you had the Copernican model. Not Kepler, but Copernicus. These two models, within basically the margin of error, given the technological limitations they had at the time, neither one could predict the future location of, say, the planet Mars any better than the other one could. They performed equally well. However, what motivated people like Brahe and Kepler to explore the Copernican model more, or at least depart from the Ptolemaic one, was that the Ptolemaic model was a pain to use. It was very mathematically intensive, and it required the assumption of many, many epicycles, many circles upon circles upon circles, about 63 in total, something of that nature. Whereas the Copernican model was much simpler and to use, particularly from a mathematical standpoint. So if you have two observations or two hypotheses that provide valid explanations, that provide explanations that are measurable, comparably measurable, then you go with the one that is simplest. 4. It's kind of already restated this, but the scientific hypothesis makes testable predictions. If you cannot test it, then in my mind, it is not science, which kind of leads me into a little bit of trouble with certain folks. Things like M theory, things like string theory, I don't believe are in fact scientific hypotheses, because from my understanding, and I could very well be wrong, but from my understanding, these theories do not provide questions that can be tested. The other one is the multiple universe theory, or multiple universe idea, where you have this patchwork of various universes within a much larger, I guess, overarching universe. But the two separate universes cannot communicate with each other. It's baked within the idea is that there is no way to communicate from one universe to the other. It's a groovy idea, and Marvel is making a huge amount of money off of it. But it's not science. You can't predict anything. You can't test anything. You can logically deduce that it makes sense. It could be logically consistent. But as Galileo showed, logic isn't the mother of science. You need to be able to test it and actually come up with it. This lecture is brought to you by Mellow Yellow. This last one isn't really a hallmark of science per se, but is at the core of how astronomy works and how we. It is a core principle that without which astronomy would be useless or could not be done. And that is known as the cosmological principle. And it has two parts to it. The first one is there is nothing special about our place in the universe. Again, as I mentioned before in the previous lecture, humanity has always had this sort of anthrocentric viewpoint where we believe that we are the center of all things, that we are the reason for creation, that sort of thing. What science tells us, what astronomy tells us, is that's not true. That there is no preferential point in the universe, be it space or time. And what that leads into, and then the second caveat is that the physical laws which govern everyday life here are the physical laws that govern everyday life everywhere else. Again, if that weren't true, that would indicate that there is a special place in the universe where a certain set of laws works, but they don't work elsewhere. So again, no special place. What this allows us to do as astronomers is that it allows us to say, all right, we have great confidence that based on observations of objects close to us, based on observations of stars near us, we have confidence in how these stars generate their energies. We have confidence in how these stars evolve over time, why some of them pulsate. And so given that confident data, those confident experiments, those observations that we made, we can then sort of extrapolate and say, all right, a galaxy that is billions of light years away from us, those stars must be doing the same things as the stars that are local to us. That's the core of the cosmological principle. We have to make the assumption, and it is a critical assumption, we have to make the assumption that the laws of nature, the basic concept of reality is the same here as it is elsewhere. If not, if we don't have that assumption, then really there would be no way for us to say with any confidence that what the stars are doing out there. So far, we have not encountered a problem with this. We have never encountered a situation where the cosmological principle seems to be invalid as an assumption. So, I'm going to talk about the scientific method. Now, every science class that I had from high school to undergraduate inevitably started out with something called the scientific method. There was a point where I hated the damn thing, because I always thought that the scientific method really was fake or false. Like, no one actually used the scientific method until I was really challenged to think about this more recently within the last few years about how do I actually do science. And the reason for this is that the scientific method is a framework. And it's rather a loose framework. There are folks that I've encountered who hang on to it very tightly as if it's biblical. Talk about independent variables and dependent variables and things of that nature. But the fact of the matter is, scientists really don't view it in that way. You can, when I went back and looked at my work, I was like, oh yeah, that would be considered an independent variable. Oh yeah, that would be considered dependent variables. So in that context, in the scientific method is really just a method. It is essentially, shall we say, a construct on how science is done. It is a roadmap, as it were. And the first thing that you want to do with the scientific method is you have to ask a question. Why does the sun rise in the west and rise in the east and set in the west? Then you have to come up with you have to come up with you have to see something. You have to experience a phenomenon, such as you see the sun every day rising in the east, setting in the west. Then you come up with a question. Why does it do that? But the question has to be testable. So your question might be, the sun does that. I believe the sun does that because the earth is stationary and the sun revolves around us. you then need to make a prediction. You then need to figure out some way of testing whether or not that's true. You can say, look at, for example, stellar parallax. You can look at a phenomenon and see whether or not the stars wiggle periodically. If they do, then the idea that the Earth is stationary doesn't work. Those two things are incongruous. One cannot happen with the other. But the point is, you would develop an experiment such as, I'm going to look at these stars. I'm going to see if they wiggle. Because I think it's the sun moving, not the Earth, my prediction is that the stars will not wiggle. And then you test that. You actually make those observations. You measure the positions of stars over time, and you see whether or not it does. In the case that I've outlined, you're going to see wiggly stars. And so in that case, you're left with basically in this flowchart kind of thing, which you probably can't see very well. But if the hypothesis is false, if the test illustrate or indicates that your reasoning is flawed, then you can do one of two things. You can either throw away that idea entirely, or you can revamp it in some way. If it's true, then you move on to the last part. And this is a part which is so overwhelmingly not talked about, I guess, not emphasized. And that is, you got to tell somebody. When I go through my classes, when I talk about the history of things, like, for instance, I will say that Hipparchus gave us the first catalog Hipparchus cataloged the night sky. But I always couch that by saying Hipparchus was the first one to write it down. He may not have been the first person to actually look at the night sky and say, oh, all the stars are in these certain locations, all the stars are at these certain brightnesses. But he was the first person to write it down so that future scientists could take that work and grow off of it. And also test it and retest it. Because as I said, scientific knowledge is provisional. It is constantly being challenged. Should I be wiggling the independent variable? Yeah. So let's go through. Let's make sure. Yeah. Let's go through a case study of exoplanets. And I have a meeting in about 15 minutes, so I will go through this. Hopefully, I will go through this quickly, but hopefully intelligently. So there have been few speculations from hundreds of years ago that exoplanets existed. So the idea is that there are said, hey, there are planets going around our sun. And then they ask the question, are there planets going around other suns? We see other stars. Are there planets going around those that we cannot see? Perhaps the most famous one is by Giordano Bruno in 1600. And he says, quote, the space we declare to be infinite, in it are an infinity of worlds of the same kind as our own. Newton, about 100 years later, uses a very, very similar bit of logic. And he says, quote, and if the fixed stars are the centers of similar systems to our own, they will all be constructed according to a similar design and subject to the dominion of one, meaning God. The basic idea here is that regardless of who built it or why it was there, if you have a scenario of planets going around our sun locally, and you see other suns, then it should follow that given that the laws of physics are invariant anywhere in the universe, that the same thing should happen around those other suns. If planets formed around the sun, then planets should form around other stars in this very similar way. The problem is that these really didn't get elevated to hypotheses until about 1952 by a gentleman by the name of Otto Struve, who proposed something known as Doppler spectroscopy as a method for detecting stars. The idea here is that he's using the what we call the Doppler effect. Now, most people are familiar with the Doppler effect in terms of sound, but it also affects light. I'll be getting into this more in specific later on, but for now, let me just say that if light is traveling towards you, if an object is emitting light and it is traveling towards you, you will observe that light as being slightly bluer than it was when it was emitted. In the case that the emitting object is moving away from you, that light will be redder. So in this case, what we have is a scenario where you have a star and a planet that are locked together by their mutual gravitational attraction. And unlike what you might think, where, say, the sun is fixed in space, it's not. The sun is going to wobble. It's going to move as the planet moves around it. While gravity attracts the planet to the star, gravity also attracts the sun to the planet. And so it causes both of those objects to move commensurately. Obviously, the sun is larger. In this case, the star is larger, so its motion is smaller than the planet. So with Struve's method, or Doppler spectroscopy, or the radial velocity method, we're not looking at the planet. We're looking at the sun, or we're looking at the star. We're looking at the light from that star, and from it, we can infer the presence of the planet. Now, as with all scientific endeavors, you're going to have failures. You're going to have false claims. And really, in this, there's a lesson to be learned. So let's take the first case that I'm aware of. And that is when William Jacob and Thomas C. claimed that they found the first dark body or planetary object in the binary system of 70 Ophiuchus, or 70 Ophiuchi. The idea here is you have two stars that are going around each other based on their mutual gravity. In that case, if you have two objects in isolation, their motion is as regular as a clock. The period of one eclipsing in front of the other is probably the best clock that we have in the universe. But it has to be in isolation. If there is another body throwing its gravity around, it's going to cause that period to change over time. It's going to cause those eclipses to change over time. And so what Jacob and C saw was that 70 Ophiuchi did not behave regularly. It did not behave as if there were two objects there. So they proposed the idea that the only explanation that they could see that they had to explain this was there had to be a third gravitational body that was affecting it. That there was a third gravitational body somewhere in that system that would explain the observations that they were seeing, these delays or these changes in the periodic nature. Well, a gentleman by the name of Moulton, Englishman, I believe, demonstrated through using mathematics analytically that if you put any mass into that system, as described by the masses of the stars, their separations, their speeds, if you put any mass in there, the system would fall apart. It would either the two stars would become unbound and they'd fly away from each other, or the two stars would slam into each other. Any third body would basically cause that system to destroy itself in one way or another in very short order. So essentially what Moulton says, sorry guys, it's not a planet causing these observational discrepancies that you're seeing. The lesson here is that Thomas C. didn't take that very well. William Jacob said, oh, okay, well, that sucks. I was really hoping we'd find a planet. And then he moved on and, had a fairly successful career. C, on the other hand, said, nope, I'm rejecting that. I am saying no to your argument or no to your work. And I'm going to continue to say that there is a planet there. he rejected the notion that is key to scientific discovery, that you can be wrong. That if there is compelling evidence to suggest that your conclusion is wrong, you really need to listen to it and accept it. Or you need to come back with even more compelling evidence. C didn't. He basically just stuck to his guns and was ostracized by the astronomical community. The most unfortunate sort of example of this was done by Peter Van de Kamp, who is was a prominent astronomer of his day and is still to this day one of the big hitters, I guess, as it were, in the field of astrometry. Van de Kamp was very good at finding the precise locations and the precise proper motion things in sky. He was kind of, I wouldn't say he was a celebrity, but he was a big name. You know, when Van de Kamp said something, people listened. And so he used the Lowell Observatory. What he noticed was he was looking at Barnard's star, which is the star with the largest proper motion, meaning if you look at it, it is the fastest moving across space relative to the other stars than any other star in the universe. Unlike what it appears, stars are not fixed. Stars actually do move around relative to each other because they all have their own peculiar motions. And so Van de Kamp was looking at Barnard's star and how it was moving, and and I'm showing the data that he collected. And what he noticed is a wiggle. He noticed that RA, which stands for right ascension, you can think of that as stellar longitude. Declination is stellar latitude. And you notice that there was shifting, that the stars seemed to be moving in RA and Dec. Not just from left to right, but also for up and down. So there was a wiggle there. Something was causing Barnard's star to move one direction and then back in the other direction. Now, if you remember from the radial velocity argument, that's gravity working. There must be something, if that is true, then there must be something gravitationally causing Barnard's star to move from one side to the other and back again. And so when Van de Kamp said, hey, I have found a planet around Barnard's star, like I said, everyone listened. They stood up and they basically dropped what they were doing. They pointed their telescopes at Barnard's star. And now comes another piece that is vital to scientific inquiry. Replication. An independent source or an independent group of scientists must be able to replicate what you saw, or must be able to replicate what your experiment has shown. And they must be doing it, and they must do this using an independent set of equipment. So when the astronomers around the world looked at Barnard's star and did not see what this phenomenon, they basically said, Peter, sorry, but I don't know what you're seeing, but it ain't there. Van de Kamp made these observations close to the end of his life, and so he was very much like C. He rejected the notion that I'm right, everyone else is wrong. But as I said, he was near the end of his life, and he'd done so many phenomenal things prior that people just kind of said, Peter will be Peter. Now, what we suspect is that there were oscillations in the telescope that he was using. Essentially, what he was seeing was some kind of periodic systematic error within his equipment. Something in his telescope was vibrating. Don't know exactly what, but that's the best explanation we have for it. Because again, every other telescope doesn't see this phenomenon. So what about detections? Eventually, we now know there are exoplanets. There are planets going around other stars. And actually, there are quite a lot of them, to the point that we now believe that there is a planet, at least one, going around every star in the universe. Or at least there was. The star could have evolved and eaten those planets at some point, but planets are ubiquitous. They are a natural formation mechanism, or a natural process of the overall formation of a star and its surroundings. But the first one, the one we confirmed, and what I mean by confirmed is that the first scientist looked at it and said, hey, this looks like a planet. And someone else looked at it and said, hey, I agree, this looks like a planet, was in somewhere that we did not expect at all, which was just fantastic. We saw planets the size of the Earth down to the size of comets, not really planets, but comets, around a pulsar. A pulsar is a dead or a stellar corpse or that spins at a very, very high rate of speed. And again, in isolation, this is the best cosmic clock. That rate of pulsation is perfect. The only way that it's not perfect is if there's something tugging on it. And that's how they were able to find Earth-like, Earth-size, not Earth-like, but Earth-size planets going around a pulsar. In 1989, David Latham's team found a planet going around, a Jupiter-sized planet, going around a system known as Gamma Cephei A in 1989. But because of the way that science works, it wasn't confirmed until 2002. So if you were to Google the first planet around a sun-like star, you're going to get 51 Pegasi b. In actuality, it's David Latham's planet, Gamma Cephei AB. But this shows you the importance of the scientific method. Dr. Latham's data suggested the presence of a planet, but it was very, very dirty. It was very noisy. In that the scientific community looked at it and said, no, there are too many other things that could produce the data that you're seeing. The star, the inherent variability of the star, just noise within your detector, systematic errors within your detecting system. It wasn't until people followed up in 2002 with better equipment that they said, oh yeah, you're right, that's a planet. But in 1995, using Struve's method, which I just highlighted, also David Latham used Struve's method, the radial velocity method. A group found I cannot pronounce the first person's name. Starts with a Q, QE, something or other, QUE, something or other, and Mayer. To be a barbaric American, I really have a hard time with foreign names. Anyway, they found a planet around 51 Pegasi, and they discovered it, and it was quickly confirmed by others in 1995. And so this was the first planet that was discovered around a sun or a star like the sun. It's basically the same age, same temperature, same size, same mass, that sort of thing. Again, because science is awesome, it was the planet that was discovered is unlike anything we could have ever even thought of or predicted. So in the solar system, the closest planets are rocky, and they tend to be a bit tiny. Then as you move out, you get to the gas giants of Jupiter, Saturn, and then the ice giants of Neptune and Uranus. Or Uranus is then Neptune. What we found, or what they found with 51 Pegasi b, is that, and also Mercury is about 4/10 of the distance away from the sun as the Earth is. So if the Earth is at 1 astronomical unit, then Mercury is at 0.4 astronomical units. This planet is half the mass of Jupiter, so basically half of Jupiter, half the size of Jupiter, orbiting around at 10 times the proximity of as Mercury. It's 10 times closer to its host star than Mercury is. So we got a massive gas planet going around its star with a year of 4 days. 4 days. It takes 4 days for this thing to go around the sun, the star. Blows my mind. No one thought this was possible. One, there's no way in hell that this thing actually formed where it was located. There was no one even thought that a planet could survive the amount of solar radiation that it would experience at that location. It radically changed. It caused a mini revolution in planetary science. in that we had this nice theory as to how the solar system kind of came into being. This kind of threw a wrench into it for good, which is good because now we have a much better understanding of how things came into being. All right, because I do have to go in about 10 minutes. What I want to say is fairly quickly is that science, as I said, is provisional. Its biggest vulnerability is its greatest strength, in that it can be proved wrong. Science can only progress if it acknowledges that it can be proven wrong and someone does that. So, for example, classical mechanics. Classical mechanics is great for about 300 years, 400 years, 300, well, somewhere in there. Since Newton to Einstein. People loved it. It's like, all right, this every phenomenon that we've seen, classical mechanics can explain what's going on. And then came things like the orbit of Mercury, which the orbit precesses with a very certain small amount, which Newton would have no explanation for. Maxwell's concept of light really didn't play well with classical mechanics, and so Einstein came along and radically changed the way that we thought about how gravitation, what gravitation is, and how it affects things. And we have since moved on. In some cases, a scientific revolution will completely erase what was before. So with the heliocentric model, we now know that the Earth is not the center of the universe, not the center of the solar system. So the geocentric universe was pushed to the wayside. It's not used in any way. But in the case of with relativity, what we find is that classical mechanics is still useful within certain regimes. If you have a certain precision limit, if you can only identify the motions of things to within, say, a meter or a meter per second or something like that, then classical mechanics will give you a good prediction. If you're worried about stuff even more precise than that, then you've got to worry about a full relativistic treatment. So classical mechanics is still around. Newton's work is still around and still taught, because it's still useful. If you want to build a building, you don't solve Einstein's field equations in order to do it. Classical mechanics still gives you a great tool for it. Last thing I want to talk about is correlation and causation. Correlation does not always mean causation, but in some cases it does. I'm looking at you, climate change. What we're seeing here is a plot of the temperature. What's the word I'm looking for? Oh no, that's not the anomaly. That's the actual temperature. So they took when, maybe 1940, and basically said, all right, we're going to take this temperature and we're going to use it as our fiducial point. And so the blue indicates that the global temperature was cooler than that point. Say, I think at this point it's 57.6 degrees Fahrenheit. So blue indicates that it's colder than 57.6. Red indicates that it's hotter over time. That black line indicates CO2 concentration, how much carbon dioxide there is in the atmosphere. Again, over the same time. And we see a definitive correlation. We see that as with a low CO2 concentration, the Earth is generally speaking colder. With a higher CO2 concentration, the Earth is warmer. Now, there are a couple of things here. First off, climate change is not thought to be true because of this plot alone. This was sort of the first indicator that people were really looking at, and taking very seriously. And there are other indicators that have been used to show that climate change is actually happening. But there's also something else, which is related to something we call cherry picking. Now, folks that like to deny science or deny the current scientific viewpoint will choose cherry picking. They will pick what parts of textbook they like. They will pick parts of graphs that they like. and ignore everything else, even if it completely contradicts what they want to say or what they believe in. Here, what we're looking at is the same plot. Basically, we're looking at the temperature, which is the blue squiggly line, over time, and the CO2 concentration over time, over that same time. And what we see here is that causality, that correlation breaks down. CO2 concentration rises with temperature or rises with time. The CO2 concentration fluctuates, the CO2 concentration continually rises, whereas the temperature goes up and down. So sometimes it's correlated, sometimes it's anti-correlated. The difference between these two things is the time, what they looked at. Here, the time was chosen very specifically, 1880. I'll give you a second to try to figure out what in history happened around 1880, specifically in the UK. If you guessed the Industrial Revolution, you are correct. When the world moved from a primary plant-based energy production system to a fossil fuel-based energy production system, that is where, and that generates a lot more CO2, and so that is a valid point from which to look at. This plot starts in 1955. Other than the Korean War, I have no idea what was happening in the world of any significance during that time. And the Korean War certainly wasn't going to be a contributing factor to this discussion. So there's no physical reason to look in that region, for this time range. The only reason to get this time range is to illustrate that, yeah, if you look in small time scales, that correlation isn't perfect. But if you look at it over the appropriate time scale, it kind of is. But correlation does not always equal causation. My favorite piece of this is sunspots and Republican senators. This is a bit dated now, but from 1964 to from 2002, you could correlate the number of sunspots seen on the sun to the number of sitting Republican senators. And there was even a time where basically the sunspot cycle will actually flip. Even given that flip, that correlation was, I guess it was the Industrial Revolutions in the 1750s. I guess they didn't go back far enough. I'll have to look into that. Thank you for pointing that out. I can assure you that correlation still works. But anyway, here you have sunspots and Republican senators. You can see that the correlation is not perfect, but it is pretty damn good. It is pretty damn close. And obviously, there's no physical mechanism here. But what we're saying is that sunspots do not magically influence people's minds and make them vote more Republican than Democrat. And we're also not saying that, as much as we would like to believe it, Republicans are not reptilians. They're not some kind of alien race that is also affecting that can affect the sunspot, the sun's activity based on whether or not they're elected to government office. All right, and with that ends my the lecture for today. And so I will cut off. Like I said, I have a meeting in about 2 minutes. She's probably right outside my door. So I hope you all enjoyed this. And if you have any questions, sadly I can't. Sadly, I cannot stick around to answer any. But if you have any questions, please feel free to leave them in the comments, or feel free to email me at parksj762@gmail.com. All right. Peace out, guys. Clear skies.